Hello everybody. We are going to continue with the topic of property testing, and in particular we're going to look at a new technique called the enforce and test technique. But before we get into that technique, let's briefly remind ourselves about the property testing context. Uh, the, uh, the motivation for this computational model comes from the fact that much of today's data is actually stored in large data centers or clouds. And when we want to perform some computation on this data, we don't have immediate access to the data as in the traditional setting where the data is residing inside the memory of the computer in which the computation is executing. Rather, the data is available only through some interface, and we can access the data only via queries and get the response to these queries and then perform the computation based on just our knowledge of the data through these queries and responses. Unfortunately, many of the types of computation that we are interested in might require a lot of information. So for example, if we wanted to find out whether a graph is connected, we only know of a few guaranteed ways to do it, and all of them require getting to know the entire graph. But on the other hand, we've had some very good success in testing whether a graph is connected uh, by making a few simple assumptions that are quite um, reasonable in many applications today. And the assumption is that the data comes with a promise. It either has the property that we're interested in, or it is far from having the property that we're interested in. And if you're wondering why this is even useful in today's context, just think about situations like recognizing someone's face. Either the photograph is that person, or it's someone completely different and therefore completely far away from that person. And many such applications abound. So we're not going to worry too much about that, but we're going to embrace this promise type of problem, knowing that A, it's realistic in many contexts, and B, it opens up some algorithmic possibilities that do not exist in traditional algorithms and traditional computation. So that's the good news that motivates this study of sublinear algorithms that focus on algorithms that run with just little of n number of queries into the data set. This new technique that we're going to talk about, the enforce and test technique, isn't really new to us. We've actually encountered it in some slight way a little while ago. All you have to do is recall the birthday paradox. We were in the balls and bins setting, and we wanted to prove that when about 2 square root of n balls are thrown, each uniformly at random, into n bins, then with some good probability we're likely to see some bin having more than one ball in it. And in order to prove this, there are several other ways to do it, but there was one very intuitive way in which we approached this the analysis of this setting. What we did was we first threw square root of n balls, and we just assumed there was no pairing of balls, no bin with more than one ball in it. Okay. Well, if it did end up having a second ball, then the theorem is only strengthened. So we place the first square root of n balls, and this imposes a structure that we can then exploit. So the first square root of n balls means that when they are thrown into the n bins, means that square root of n bins are non-empty, and every subsequent ball that is thrown has a 1 over square root of n chance of falling into one such bin, and that's what we exploited. And this, if you just think about it, the first square root of n balls just enforce a certain structure, and the second square root of n balls exploit that structure. And this is the general paradigm of this enforce and test technique. But we need to be a bit careful about this. So let's think through this carefully. Now let's say this rectangle here represents the universe of all legal inputs, and within that we have a set I, and this is the set I of inputs that are far from having the property that we are interested in testing. So when we get an instance from this set I, we must reject that instance with a certain amount of probability, or in other words, we must only accept it with some small probability that's at most some p. Okay, and then let's say we do manage to do that. Okay, now we need to extend that to prove that no instance I is accepted with any reasonable probability. So well, what are the ways in which we can do that? We can use the union bound. So we can say, okay, if this one instance is not accepted with probability p, then all of these instances are also not accepted with probability that's equal to the cardinality of the set I times p. Okay, but that's too weak, because if p is, for this case, I mean, the set I is going to be quite large. It's typically exponentially large, and so the probability p has to be exponentially small in order for this union bound technique to work, and that's usually not the case. So this approach is too weak. So this is just a sort of a motivation for why we need the enforce and test technique, because now we ask, what do? We seem to be stuck. So let's think about this. What we do, the way we get around this is, as we did in the balls and bins case, first try to enforce some structure. And this can either be done in the context of the algorithm itself. So this is if the algorithm does it, we can think of it as a sort of an explicit enforcing of the structure. Or it could be done in analysis, where it's a little bit more implicit. The first few queries enforce the structure, and it typically enforces the structure into instances that must be accepted. And then we test against that enforced structure. In other words, we are searching for violations, because once the structure is established, then it becomes easier to test and find out ways in which that structure gets violated. And if it gets violated, well, we know the answer. We have to reject that instance. But if it is not violated, then we accept. This is the general approach we take in the enforce and test technique. Okay, so without further ado, we will now look at a concrete example where this enforce and test technique is exploited.